All right, so picking up where I left off last time with some more additions to this generalized Dijkstra code. So a couple of ideas that I'll sort of be throwing around. One is to replace the hashable constraint with orderable constraint to use instead of using a hash map in here, just use a normal map. I'm kind of curious how well that will perform. Because even if it doesn't perform as well as using the hash set, there's still the matter of like ord is a stock derivable type, whereas hashable is not, and that can can potentially create a lot of friction for users. So I'm curious. I want to just not benchmarks, but the tests do take. That's not right. This one at least works. So we can see these values, and these can maybe serve as a guide here. I'm just going to go ahead and just copy these to a notepad. And just see if it's entirely possible that ord will actually be faster. And so I want to try ord. So what if instead of using hash map, I just say map. As m. And what instead of hash set, I just say data.set as us. Alright, and now we play the game called Follow the Compiler Errors. It's taking a while to compile some of these modules, which is kind of interesting. So there's not that much code in them, but maybe there is. I don't know. Well, duh. Data.map does not import hash map. Duh. And data.set does not import hash set. So it's actually, in these cases, easier to just go into GHCI. Wait, what? Oh. And just do a reload. Alrighty, so... What? Why are you... That's weird. Anyways. Okay, so this is m.lookup node name. Adjacency list. Call this just a map. 92. M should be H. No, it should be M. $92.79 should be S dot number. 76 should be S dot insert. 72 should be S dot member. 67. Oh darn, this is annoying part of using a floating terminal. I don't want to use a floating terminal, but I forget what prompted me to do that. Still need to spend some time. Maybe one of these days I'll just spend a stream doing nothing but just dealing with my IDE. my IDE. I actually have some vague plans to do a series on IDEs and why it's important to do good things with your IDE, which I have never done for my Haskell stuff, which is bad. Okay, 52. That exists. 51. $49. What the? Okay, could not deduce ORed, so I have to change all these hashable constraints to use ORed constraints instead. This is ORed. Okay. Oh, look, the code compiles. That didn't take long at all. All right, let's see how it compares. These are sort of original benchmarks to test. Wait a minute. Oh, that's right. So my test code will also need to change. Okay, so let's compare these against the benchmark. It actually does look like the hash set did have slightly better performance overall. So this is about the same. This is twice as much. This is about the same. Yeah, so across the board, especially in these last few cases, it's definitely improved performance with hashing. So yeah, that's an interesting question. Maybe if I were to try and make this into a package, I would put them in separate modules and just say, you know, I'm curious, is there like Haskell algorithms? Like, is there like an algorithms package? Algorithm design, the algorithms / Haskell. What is this? Doesn't look like a package. All algorithms implemented in Haskell. I'm actually curious about this. Unless I misspelled Dijkstra, I don't. Tutorial graph distance, I see. That's probably. That's not. Nope, that's a very different graph distance. DFS, okay, directed graph. So this isn't graph dist again. Okay. So this repository that happens to come up isn't actually the most exhaustive. It's fairly recent as far as Haskell things go. Last update was March 2021. So that's not actually, this is the thing I'm looking at. Algorithm design with Haskell book, maybe an old book. I don't know. Curious how old this is. 2020, that's actually pretty recent. Maybe that'd be worth a read for me. This is another thing that comes up in the Google search. Data structures and algorithms for working with 2D graphics, that's specific. Haskell. It's not an ad, so no one's. It's interesting. I'm just making business notes here. Yeah, so it's definitely, you know, there's not like a central package or anything. So I wonder if there's space for this. anyways, just a thought I had. Because I think I would make modules that are like algorithms.dijkstra. And then just normal, and then algorithms.dijkstra.ord, just in case someone wanted to use ord. But anyways, so what did I want to do next? So I've tried out make it deplorable instead of hashable. The real trick, which I have sort of next on my list, would be to allow both of them on the same piece of code. So there are the same sort of thing. And say like, oh, if we have this constraint satisfied, dispatch to this implementation. If we have this constraint satisfied, dispatch to that implementation. I don't know if that's... I'll have to do some thinking about whether that's even possible with dependent types, or Haskell's version of dependent types, or if there's some way to do that. It's an interesting problem. I would probably, I think as a first pass on this, I feel like making different modules is an entirely acceptable solution. Okay, so allow returning the full path, I think, is fairly important. Debugging, the other note I'm going to put here, monadically? I don't know if that's actually necessary. I mean, I would want to have it monadically if I wanted someone to, like, if I wanted to insert debug statements into this algorithm itself. I'm not sure if that's actually necessary. I'm going to take that out. Debugging would be like, the purpose of debugging would be like, or maybe this connects with monads, because like with my previous attempt here with this hilarious function, like what I return, I return the cost and the new state and a string, and the string is sort of debugging information so that I can just sort of print this out and be like, oh, look, this is what happened. Because I think that is kind of, maybe again, that would be a separate module. It'd be like, okay, if you provide me with this family where our function can also return a string, then I will let you, I will give you the final path that includes like a string description of it. But at the same time, it's also, I don't know, I think that's something a user can do in post-processing. Well, actually, I don't know about that, because in this particular version, saying like it's much more concise, like the move itself can be much more concisely described when both states are visible rather than one state. But then again, I don't know. It's an interesting question. I'm not sure it's necessarily worth, if I were to package this up, I'm not sure, and like try to put it on a package or something, I don't know if it would be worth it for that. So anyways, let's just work on having something else here where it's just going to be, okay, find shortest path. And this is going to have basically the same gigantic type signature, except it's not merely going to return the distances, also going to return the list of Dijkstra node state, Dijkstra node G. It's going to return all that, and in fact, we're actually going to take the sort of simplest way to do this is that we're going to take this implementation this loading. Well, let's go to 57. Distance, find shortest path. I want to find shortest path. It's going to be the same thing, so it only returns the path. Equals, what are our inputs again? First dot. Is it not that? Second dot? Probably. Should work. This one is going to end up being first dot. All of this I had one job and I put it in the wrong place. There we go. Is that, except take process Q. Now, basically we're going to need to augment the Dijkstra state. So this I can actually say is undefined for right now, just for the moment. I'm really annoyed at that cubes module and the lid module for taking so long. Oops. Let's keep it now. Oh, it doesn't actually work the way I wanted it to. Darn. Anyways. Are you going to give me a length suggestion here or not? I guess not. Okay. Pick match expected type. A to C. First. Oops, this should not be a first. That's fine. Okay. So, what needs to change here? So, what was this? This was process Q. This, and then we had like this. So process Q, the initial state, what does it look like? We have our hash set, which is s.empty, and our we have our initial Q and dist. Everything okay. S.empty, hs.empty. So how do we create this list? Our Dijkstra state needs a mapping. It needs one more mapping from nodes to nodes. So let's go ahead here. That's okay, crap. We need another element which is going to be hash map from n to n, I think. And initially this is just going to be, I think it is actually just going to start as empty. Because basically, okay, so what is the manner in which this map works? We have the destination will be the key, the source will be the value. So it seems a little bit backwards. So every time we pull something out, then we save its source. Like we get on here. We're saying, okay, we are processing. Now we do this. Okay, we pulled out chord out of our visited out of the heap. So chord and mindist have been pulled out. And now we say we are officially visiting chord. Except that, well, here's the interesting thing, because with Dijkstra's algorithm, this might actually be different than it is in other algorithms. I think we might actually want our heap to contain the parent information for us in this particular case. Like what we might actually want is like we might want the coordinate and its parent, like here. Because when we insert, so filter, and we fold out, fold neighbor. So with each neighbor we insert into the heap, like the same thing could be inserted into the heap multiple times before we are able to really, what should I say? Before we're able to determine like what its parent really is. And so I feel like we need the extra information here of, you know, chord 1 and parent. Does that make sense? It's a little weird. Because it makes sense here that we're saying, okay, we're going to drop this chord, and then we just proceed. Otherwise, we insert it as visited and insert parent. So we say, for example, so okay, so parent 0. No modifications in that case. So we say, for example, hm.insert let p1 parent 1 is equal to hm.insert, and who are we inserting? Here we are inserting chord parent 1. Now, what needs to be done here? So that means is our heap now, it maps from distances to pairs. But could be nothing, because it could be the start of the path. And I'm not sure if there's a better way to handle that. I mean, I'm trying to decide if this needs to be a maybe n, or if it, because it's equatable, because we have the EQ type class, I assume at this point, I've lost track of how many type. Actually, we don't have it. We have or. It would be easy enough to add. We don't technically have that constraint at this. We have. No, here it is. Okay, equatable Dijkstra node G. We could say if it's equal to itself, if it's equal to its parent, and so our initial thing is actually just source. What that means is a prio heap actually contains n. That's correct now. Pulling it out is correct, and so now when we do h.insert, all we have to do is say C2, C1. Now within this particular, we don't modify p in this particular function. We only modify it up here when we pull it out of the queue. But this might, wait, I put V1, that's not right, C1. Because this was our parent, right? We say fold neighbor chord. Chord in this case is the new parent. And C2 is the new neighbor, which may potentially have C1 as its parent. So let's see if that compile would have been very unlikely. Made a lot of refactoring changes. Wait, what? P1? No, P0. What? Not 0, 0. Okay. Now you're a little confused by this, which is understandable. Because there's going to be this, and then we're going to have to unwind the map. This actually kind of makes sense to me. We have our distance. And then what is it complaining about here? Oh, I didn't define this properly. I didn't redefine this. Okay, now it compiles. So we actually might be really close here. We just have to say, unwind path. This is a function I've written a dozen times before in various ways, but never quite in this kind of generalized way. Unwind path. What does this take? It takes our mapping. So our hash map of nodes to nodes. Dijkstra node G. And it returns. So source and destination are in scope here. And so what does it do is it returns list of Dijkstra node G's. And we actually want to do this in a tail recursive fashion. So, okay. Oh, do we need an extra argument for the current? No, because we can just start with destination. Yeah, we can just start with destination in the list. It's easy enough. We'll just have to have this edge case. This shouldn't happen. Parent map. Parent map, so current. Do we need rest here? Probably. Well, So we're going to say case, turn that lookup current parent map of if we get current back. We actually ought to be able to. Yeah, it is better to do nothing. Nah. Otherwise, I have to adjust everywhere, and that's just annoying. So it's nothing. Then let's say reverse. Actually, wait, no, we don't even have to reverse it. Actually, we're sort of doing the reversing as we go. Just current also gets itself just other node. This pattern match probably works. I'm not sure. We'll have to see. Just other node. We need to recurse somehow, and we're going to say unwind path, parent map, and it'll be other node. Okay. Let's see if it's happy with that, or if I need to do an if statement. Pattern matches were done. Oh, okay, so this isn't going to work. Just node. We have to say if node equals current, and a hum else. Else unwind. A variable not in scope other node because I need to do node. So we have that, and then over here we just say unwind path. Well, okay. Say what? Final state is equal to process Q. All this jazz. Oh. So the final state, and by final state, of course, what I mean is just gonna do this immediately. We don't care about visited, we don't care about the heap, we just want final list map, parent map. And so therefore we just have final distance map on dest, and we have unwind path final parent map, unless there's another edge case here where we have to think about what if a path doesn't exist. We want to return the empty path. So is this going to actually accomplish that? I don't think as written this is going to accomplish that, because unwind path can stop if it hits nothing. So I guess the nothing case does serve a valuable purpose in that if we hit nothing, how do you even hit nothing? Oh, wait a minute. First of all, unwind path needs unwind path final parent map dest. So if it never gets to source, what do we do if it never gets to source? That's sort of an issue. Final path is going to be equal to if. Oh, okay. say an unvalidated path, and that is equal to is equal to that. And then the final path is if validated path equals if null or head is not equal to source, then empty, else unvalidated. And maybe that's right, maybe it's not. I'm gonna have to end the stream before we're gonna have a chance to really test that out. Also screwed up. The process queue can't just return the hash map anymore. It actually has to return this and this. Oh, you're still not happy. One of my process queue calls is wrong. Where is it? Oh, whoops. Duh. This one is wrong. We don't need these. Okay. I don't know if my tests still work. Of course, my tests aren't really doing the thing. They aren't testing the path. We'll have to test the path tomorrow and see if I call all the edge cases there. Because there are quite a few edge cases. Especially once you start looking at the path itself. Looks like nothing's wrong with stuff so far. But yeah, like I said, path can have a lot of different edge cases. So we'll go ahead and look at that tomorrow. I'm gonna take this out. I'm not gonna worry about this. So we're just gonna do this, and I'm gonna think about what's next after we do that. So probably be on in the morning tomorrow. So see you then. Thank you for tuning in.